Welcome to Lecture 9 of our Differential Equations course. This week we're going to finish Chapter 4. We'll finish talking about the Laplace transform, and then we'll start the final chapter, which is about systems of equations. Sections 4.5 and 4.6 are amongst the most difficult sections in this course, together with the final section, which we'll talk about next Wednesday. These are perhaps the most difficult topics in this course. And then in the second half, or the final 20 minutes of today's class, we'll start talking about systems. And because we're just going to be doing an introduction, the end of today's course will hopefully be easier than the first part. So, first of all, ordinary differential equations with discontinuous forcing functions. So far, we've been looking at differential equations where the forcing function, the GT part, has been a continuous function. But that's not always what you expect to see in engineering. For example, a very simple machine, very simple example, let's suppose we have a machine which we can switch on and we can switch off. So our input will be our on-off switch, and the output will be what the machine does. The idea is if the machine is off, it doesn't move, we switch it on, it spins up, and then we can switch it off again. In terms of functions, let's suppose our machine is switched off for the first 10 seconds. There's no power going in, so the machine does nothing. The output is also 0. And then let's suppose after 10 seconds we switch our machine on. So then the input is now 1 between 10 and 20 seconds. So the output we would expect to then quickly increase up to some level. And then after 20 seconds, let's suppose we switch the machine off again. So now there's no power going in, the input function is 0. Then the output we would expect to decrease to 0. It's not going to suddenly jump down, but it will go down as some sort of continuous function. Let's start with this example. Here's our forcing function, or our input function. This one, the first example, is actually a continuous function. It's 0, and then it goes up as a linear function, and then it's equal to 1. But it's not a differentiable function. Solve y double prime plus 4y is equal to this function. And just to make this easier, we'll use the initial conditions. Y of 0 is 0, y prime of 0 is 0. Now, this function we can write in terms of the unit step function, as we talked about last time. We start at 0, so the first part of the function is 0. There is a change at 5, so it's going to be something u5, and then there's another change at 10, so it's going to be something u10. What are these somethings? These somethings are always function on the right minus function on the left. We look at this first one, for example. The function on the right is 1 over 5t minus 5, and the function on the left is 0. So we put 1 over 5 t minus 5 minus 0 here. And similarly for the final something, final jump, it's 1 on the right of the change, and it's 1 over 5 t minus 5 on the left. So we put 1 minus 1 over 5 t minus 5 just here. And we can simplify this to 1 over 5 multiplied by u5 multiplied by t minus 5 minus u10 multiplied by t minus 10. So our initial value problem is y double prime plus 4y is equal to this function with the initial conditions 0 and 0. And let me remind you of two formulae from previously. We have the shifting formula, which tells us that the Laplace transform of the unit step function multiplied by f at t minus c is e to the power minus cs capital F of s. And that's what we have here. Look, we have u5, and then the same number appears. We have a function calculated at t minus 5. And in the second term, we have the same thing. There's a 10 just here, and then t minus 10. So we can use our formula. And I'll also remind you that the Laplace transform of t is equal to 1 over s squared. So if we take the Laplace transform of our differential equation and we substitute in the initial conditions of 0, on the left side we have s squared plus 4, capital Y. On the right side, 1 over 5, because it was 1 over 5. Instead of u5, we're going to write e to the power minus 5s. Here it is. Instead of the u10 part, we would have e to the power minus 10s. And the Laplace transform of t is 1 over s. So this is all divided by s squared. I'll leave that for you to double check. Divide both sides by s squared plus 4, and we get an equation for capital Y. If we can find the inverse Laplace transform of capital Y, then we have our answer. Now, this is a complicated function. Let's make this a little bit easier. What do we need here? Or rather, what don't we need? We don't need the 1 over 5. That's just a number. We can put that in later. These exponential functions, we can put these in later. So forget about these for now. And let's suppose instead it's just 1 on the top and s squared plus 4 on the bottom. This is the function we're going to be looking at. Let's call this the function h. Then we have that capital Y is putting the numbers and the exponential functions back in. 1 over 5 e to the power minus 5s capital H minus 1 over 5 e to the power minus 10s capital H. The strategy is, first we're going to find the inverse Laplace transform of capital H, and then we're going to use our shifting formula to find the inverse Laplace transform of capital Y. So step 1, we're going to look at capital H. And then we're going to be using the shifting formula to find Y. Rearranging the shifting formula, taking the inverse Laplace transform on both sides, we can understand that if we can find small h, then we can find small y. So how do we find small h? We have to use partial fractions. I'm going to leave it for you to check this calculation. Check that capital H can be written as 1/4 over s squared minus 1/4 over s squared plus 4. So then small h must be 1/4. Inverse Laplace transform 1 over s squared, we know this. I don't want 1 over s squared plus 4, I want 2 over s squared plus 4 because this appears on my table of elementary Laplace transforms. So I'm going to take 1 over 8 outside and leave the 2 inside. We have minus 1 over 8, inverse Laplace transform 2 over s squared plus 4. And we know how to do these. The first one is just t, and the second one is sine 2t. So now we know small h. Because we know small h, we now can find small y. Here's our formula at the top. We want to do the inverse Laplace transform of e to the power minus cs capital H, and we know that this must be the same as the unit step function multiplied by h at t minus c. There's a typo here. This s should not be here. So we have 1 over 5 u5, h at t minus 5, minus 1 over 5 u10, h at t minus 10. And then we're pretty much finished. We know h, we know small h, substitute this in, and we get our answer. Small h was, in the first term, t over 4. We're going to replace the t by t minus 5, and we have an extra factor of 5 over outside, so that becomes 20. And we also had 1 over 8 sine 2t. We replace the 2t by 2t minus 10, because t minus 5, multiply that by 2, becomes 2t minus 10. And 8 multiplied by 5 gives us the 40. And then we do the same in the second bracket. Instead of 1/5 multiplied by t over 4, we replace the t by t minus 10 now, to get t minus 10 over 20. And instead of sine 2t, we replace the t by t minus 10 to get 2t minus 20. And this is the answer to this problem. Let's do another one. Solve y double prime plus 3y prime plus 2y is equal to this function, which is equal to 1 if t is between 0 and 10, or equal to 0 if t is greater than 10. So we can think of this as some machine which is switched on until 10 seconds, and then after 10 seconds we switch the machine off. Because our function is 1 minus u10, when we take the Laplace transform of our differential equation and we substitute in the initial conditions, we get s squared plus 3s plus 2 capital Y minus s plus 3 is equal to the Laplace transform of 1 is 1 over s, and the Laplace transform of u10 is e to the power minus 10s over s. I'm going to leave this for you to check. Please check and let me know if there's a mistake here. Rearranging this, we can write capital Y is s squared plus 3s plus 1 minus e to the power minus 10s divided by s squared plus 3s plus 2. We need to find the inverse Laplace transform of this function. And I'm going to do this in two parts. First, I'm going to forget about the minus e to the power minus 10s, and I'm just going to look at s squared plus 3s plus 1 over s squared plus 3s plus 2. And then in the second part, we'll just look at the minus e to the power minus 10s part. But as I did in the last example, anytime we see an exponential, we can just forget about it. We'll put the exponential function in later when we do the shift function. So for now, let's just pretend that the function on the top is 1. So in other words, I'm going to be looking at the function s squared plus 3s plus 1 over s squared plus 3s plus 2, which I'm going to call capital G. And I'm going to be looking at the function 1 over s squared plus 3s plus 2. We will find the inverse Laplace transform of these two functions, and then we'll use them to find the inverse Laplace transform of capital Y. Because capital Y is capital G minus e to the power minus 10s capital H. If we can find small g and small h, then we can find small y. So partial fractions. Capital G, I'm saying, is the same as a half over s plus 1 over s plus 1 minus a half over s plus 2. And I'm saying that capital H is the same as a half over s minus 1 over s plus 1 plus a half over s plus 2. And please check this for me. Assuming this is correct, it follows that small g is a half multiplied by 1, because the inverse Laplace transform 1 over s is 1. The inverse Laplace transform 1 over s plus 1 is e to the power minus t, and the inverse Laplace transform 1 over s plus 2 is e to the power minus 2t. And likewise, for small h, I get a half multiplied by 1 minus 2 times e to the power minus t plus e to the power minus 2t. Now that we know small g and small h, we can find small y. So I've put these at the top. We've found these. Now we're going to do the key step. Now we're going to be using the shift formula. I want the inverse Laplace transform of capital G minus e to the power minus 10s capital H. And by the shift formula, that's small g minus u10, small h at t minus 10. Small g, we can just substitute in. For small h, I have to replace every t by t minus 10. So it becomes minus t minus 10 and minus 2 t minus 10. Let's do another example. This is almost the first example which I showed you with a picture. Solve y double prime plus 4y is equal to u pi minus u3 pi. Our input function starts at being equal to 0 until pi, then it jumps up to 1, and then it jumps back down to 0. So we might think of this as we have a machine which is switched off, then we switch the machine on, and then we switch the machine off. And we ask, what happens to y? So what do? We start by taking the Laplace transform of the differential equation. Because the initial conditions are just 0, the left-hand side is just s squared plus 4 capital Y. And on the right side, we get e to the power minus pi s minus e to the power minus 3 pi s divided by s. Divide both sides by s squared plus 4 to get our formula for capital Y. Now what do? We ignore all the exponential functions. Ignore e to the power minus pi s and ignore e to the power minus 3 pi s. Let's just suppose we have the number 1 on the top here. I want to find the inverse Laplace transform of 1 over s squared plus 4, and then I'm going to deal with the exponential functions later. So let's call this function h. First, we'll find small h, and then we'll use that to find small y. How do we find small h? We use partial fractions. I'm saying that small h is the same as a quarter 1 over s minus a quarter s over s squared plus 4. So in other words, we have a quarter multiplied by the Laplace transform of 1 minus a quarter multiplied by the Laplace transform of cos 2t. So of course small h is then just a quarter minus a quarter cos 2t. Great, now we know small h, we can use this to find small y. We need to find the inverse Laplace transform of e to the power minus pi s capital H minus the inverse Laplace transform of e to the power minus 3 pi s capital H. So we use our shift formula. This is the same as u pi, h at t minus pi, minus u 3 pi, h at t minus 3 pi. And that's what we need. We just need to take our function of h and substitute it in here. First, we'll replace every t by t minus pi, and then secondly, we'll replace every t by t minus 3 pi. So there it is. Instead of cos 2t, we need to have cos 2t minus 2 pi. And instead of cos 2t, we replace that by cos 2t minus 6 pi. So to recap this section, the key idea is anytime we have a function like this that we're trying to find the inverse Laplace transform of, start by ignoring all of the exponential functions and just pretending that there's a number 1 there. Step 1, find the inverse Laplace transform of this simpler function, and then use the shift formula to find the inverse Laplace transform of the function that you want. Our second idea for today's lesson is the convolution integral. Let's suppose we have two piecewise continuous functions. There's a way to combine these functions, which is called the convolution of these functions. And we write this as f star g, or f asterisk g. And what this means is the integral from 0 to t of f, and then a dummy variable, here I'm using tau, g at t minus tau d tau. Because we're going to be using this a lot, I'm writing this definition at the top of the slides. Now, we have a theorem which says that f convoluted with g is the same as g convoluted with f. Okay. F convoluted with g plus h is the same as f convoluted with g plus f convoluted with h. If we have three functions which we convolute together, it doesn't matter where we put the brackets. F convoluted with g convoluted with h is always the same as f convoluted with g convoluted with h. And if one of the functions is 0, if we have a 0 inside the integral, then of course we always get 0. I'm not going to prove these formulae. I don't think that's necessary for this course, but I do want to give some examples first before we start using them for our differential equations. First of all, I want to calculate cos convoluted with 1. In other words, that's the integral from 0 to t of cos tau multiplied by 1 d tau. And it's easy to see that this is the same as sine t. Then I want to do 1 convoluted with cos. The theorem says this should be the same as what we've just done. The theorem says f convoluted with g is the same as g convoluted with f. So we should get sine t again. It's the integral from 0 to 1. Now 1 multiplied by cos at t minus tau, d tau. And when we calculate this, again, we get sine t. Now, one thing to note from this example is, in general, a function convoluted with 1 is not equal to the function. Here, cos convoluted with 1 is not cos, because cos convoluted with 1 is sine. I also want to do sine convoluted with sine. So we put sine into our formula. This is the integral from 0 to t. Sine tau, sine t minus tau d tau. And I want to calculate this integral. Sine t minus tau is the same as sine t, cos tau minus cos t sine tau. Or sine t multiplied by the integral of sine tau cos tau minus cos t, integral of sine squared tau d tau. We know how to calculate these from first year calculus, so let me just skip through this calculation. And then we simplify. We get a half sine t minus t over 2 cos t. Now, sine is a function which is sometimes positive, sometimes negative. Cos t is a function which is sometimes positive, sometimes negative. This whole function is sometimes positive and sometimes negative. Don't fall into the trap that f convoluted with f is not always positive. This is not a function squared, it's a way of combining two functions. F convoluted with f is not always positive in general, as this example shows. Now, why are we talking about the convolution of two functions in our differential equations course, in our Laplace transform section? Because of this very important theorem. The Laplace transform of f convoluted with g is equal to capital F multiplied by capital G. And this is going to be very useful for us when we're trying to do inverse Laplace transforms. Because this means that if we're trying to do the inverse Laplace transform, two functions multiplied together, we could just take the inverse Laplace transform of each function separately and then write the convolution of those two functions. For example, find the inverse Laplace transform of a divided by s squared plus a squared, where a is a constant. Now what do we have here? We have two functions multiplied together. We have the function 1 over s squared and the function a over s squared plus a squared. And we know the inverse Laplace transform of each one of these. We know that the Laplace transform of t is 1 over s squared, that's the first one. And we know that the Laplace transform of sine at is a over s squared plus a squared, which is our second function. So, small h is going to be the inverse Laplace transform of 1 over s squared convoluted with the inverse Laplace transform of a over s squared plus a squared. That's our key theorem. In other words, we get t convoluted with sine at. And if we wanted to, we could just stop here. We could say this is the answer. Or we could be more precise, we could calculate this in terms of integral, and we find that we get at minus sine at over a squared. Previously, when we were trying to find an inverse Laplace transform of a function like this, we were using partial fractions. First, we split it into easier functions using partial fractions, and then we took the inverse Laplace transforms. This is another way to find the inverse Laplace transform of something like this. We could just do two easy inverse Laplace transforms and then calculate an integral. Okay, so now let's go back to our initial value problems. Solve y double prime plus 4y is equal to gt with the initial conditions y is 0 is 3, y prime 0 is minus 1. And I want to solve this for any function gt. If we take the Laplace transform of the equation, we get s squared capital Y minus 3s plus 1. That's the y double prime part. Plus 4 capital Y, that's the 4y, is equal to capital G. Or we could rearrange it like this. Capital Y is 3 multiplied by s over s squared plus 4. Okay, we know s over s squared plus 4. Minus a half, 2 over s squared plus 4. Again, we know 2 over s squared plus 4. Plus a half, 2 over s squared plus 4. I know this one, capital G. Now, inverse Laplace transform s over s squared plus 4, that's easy. Inverse Laplace transform 2 over s squared plus 4, again, that's easy. But in the third term, we have two functions multiplied together. So we're going to use convolutions. In the final term, we have sine 2t convoluted with small gt. Or we could write this in terms of an integral. For any function gt, this is the solution to the initial value problem. If later on we find out what gt is, we just need to substitute that into the integral, calculate the integral, and we've got our solution. Find the inverse Laplace transform of 2 over s minus 1, s squared plus 4. We could use partial fractions if we wanted to, but this time we're going to use the convolution theorem. We have the inverse Laplace transform of 2 over s squared plus 4, we know that one, multiplied by the inverse Laplace transform of 1 over s minus 1. I know that one. That's just sine 2t convoluted with et. And I'm just going to leave the answer like this. Or I could write it as an integral if I wanted to. Another example. Solve for y double prime plus y is gt with the initial conditions y of 0 is 3, y prime of 0 is minus 7. And again, this is for any function gt. We don't know a particular function gt, we're doing this for any function. So what do? We start with the differential equation, and we're going to take the Laplace transform of everything. We're going to get 4 multiplied by s squared capital Y minus s at y0 minus y prime at 0 plus capital Y is equal to gt. The initial conditions are 3 and minus 7. Let's put these in. Let's solve for capital Y. Let's move all of this over to the right side. And then we're going to divide by 4s squared plus 1. Here we go. We have capital Y is 12s over 4, s squared plus 1 over 4, minus 28 over 4, s squared plus a quarter, plus capital G of s over 4, s squared plus a quarter. Or to simplify this slightly, 3s over s squared plus a quarter, minus 7 over s squared plus a quarter, plus capital G multiplied by a quarter over s squared plus a quarter. Let's split it up like this. S over s squared plus a number. Okay, that's on the table of elementary Laplace transforms. That's easy. If I have a number on the top of s squared plus a quarter, the number needs to be the square root of a quarter. All of the other numbers I'll move outside. And the same over here, a quarter, so a half over s squared plus a quarter, and move the other numbers outside. The first one is just the Laplace transform cos 2t. This one, second term, we know as well. A half over s squared plus a quarter is just the Laplace transform of sine t over 2. And again, sine t over 2. We need to find the inverse Laplace transform of this. First one's easy, second one's easy. For the third one, we use the convolution theorem. So let's write it down. 3 cos t over 2, and second term, minus 1 over 14 sine t over 2, and then finally the third term, a half small g convoluted with sine t over 2. And this time, let's just leave it like this. This is the end of chapter 4, and as I said, this is one of the hardest topics in this course. If you understood the first part of today's lessons, then well done to you. Now let's look at something a little bit easier for the rest of today's lesson. We're going to move on to chapter 5, and I'm going to give an introduction to chapter 5. Let's suppose we have a dynamical system like this. I have 2 blocks which are attached to each other and attached to the walls on the left and right using springs. And these 2 masses are vibrating left and right, left and right. We can say that the mass of the first block is m1 kilograms and the mass of the second block is m2 kilograms. And we can suppose that there are forces acting on these blocks. These 2 blocks are going to move backwards and forwards, as I can show you at this web address or using the image which is in the course content section. Now, what would the acceleration of the blocks depend on? It's going to depend on the displacements, x1 and x2, how far are the blocks from their resting positions. The acceleration is going to depend on the forces on the blocks, and it's going to depend on the masses of the blocks. So we're going to expect that the acceleration of the left block is some function of x1, x2, f1 and m1, and we're going to expect that the acceleration of the right-hand block is a function of x1, x2, f2, and m2. We have a system of two differential equations. To be able to find our two functions, x1 and x2, we're going to need to solve these equations at the same time. And we will be doing this tomorrow. Let me show you another system of differential equations. Perhaps the most famous system is the predator-prey equations. dx dt is some constant x minus some constant xy, and dy dt is a constant xy minus some constant y, where xt is the number of prey and y is the number of predators. For example, we looked at an example right at the start of this course with mice and owls, where the owls were eating the mice. This is a more sophisticated model for mice and owls, because now the number of owls in the region is allowed to change depending on if they have enough food to eat. Because these equations are not linear, we have an xy term in each one, this system of equations is going to be too difficult for us to look at in this course. If you're doing a more advanced course of differential equations, you might look at this system. We're going to be looking at systems of first order linear differential equations. Now, it's possible to convert an nth order linear equation into n first order differential equations, or vice versa, and go the other way. For example, let's suppose I give you a second order linear ordinary differential equation, and I ask you to change this into a system of two first order differential equations. We need some new variables. Let's suppose x1 is the same as the variable that we already had, the u, and for our second variable we're going to choose u prime. Then clearly x1 prime is x2, and from the differential equation, u double prime is minus 0.25 u prime minus u. That's just the differential equation rearranged. So we get x2 prime, or u double prime, is minus 0.25. Instead of u prime, we write x2, and instead of u, we write x1. Now we know our two equations. x1 prime is x2, x2 prime is minus x1 minus 0.25 x2. This is how we change a second order linear equation into a system of two first order linear equations. When we study systems, we're going to be needing our linear algebra theorem. We're going to be needing matrices, eigenvalues, and eigenvectors. We're going to use the Wronskian concept of linear independence and more. So I'm going to need you to briefly revise your linear algebra theory. So please either revise your linear algebra lecture notes or read your linear algebra textbook before tomorrow's lesson, or if you happen to have the differential equations book by Boyce and DePrima, they give a revision of linear algebra in section 7.2 and section 7.3. Before tomorrow's lesson, please have a quick look through your linear algebra book, or your notes at least. Let's talk about the basic theory of systems of first order linear equations. This is a system of equations. There's n equations in n variables, and each one of these equations is a linear first order differential equation. And this is quite messy to write. Look how much text there is here. Isn't there an easier way to write a system of equations? Well, you've studied linear algebra, so you know, of course, how we do this. We use matrices and vectors. The vector bold x, or if I'm using a pen, I'm going to use underlined x, will be the vector x1, x2 up to xn. The derivative of this vector just means x1 prime, x2 prime, x3 prime, etc. Capital P will be a square matrix, an n by n matrix, where each one of these elements, or each one of these terms inside the matrix is a function, and G is going to be a vector function. Now, instead of the complicated system on the previous slide, we could just write this as x prime is equal to the matrix Px plus the vector function G. And of course, this is a much nicer way to write this. First, let's think about homogeneous systems. So first, let's look at x prime is equal to ptx. It's homogeneous because we don't have the plus g. We need some notation. In chapter 3, this should be, when we looked at second and higher order differential equations, when we had different solutions to the equation, we would write them as y1, y2, etc. But that's going to be confusing in this section because subscript we're using for coordinates in a vector. So we're going to need a new type of notation to denote the different solutions. And the notation we're going to use is superscript open bracket number. So if you see x superscript 1 in brackets, this means solution number 1. And if you see x superscript 2 in brackets, then this just means solution number 2, and so on. Now, let's do a bit of revision from chapter 3. Remember that if we had a homogeneous second order linear equation, and if we knew 2 solutions to it, then every linear combination of these 2 solutions was also a solution. We can do the same thing for our vector solutions or our solutions of systems of equations. If we know 2 solutions to x prime is equal to ptx, which is a linear equation, linear homogeneous equation, then every linear combination of these 2 functions is also a solution. So same idea as in chapter 3. So for example, I'm telling you 2 solutions to this linear system. I'm saying that 1, 2 e to the power 3t and 1 minus 2 e to the power minus t are both solutions to the linear system x prime is equal to 1141x. And I'm going to prove this to you tomorrow. For now, just assume that I'm telling the truth when I say that these really are solutions to this system. Then that means that every linear combination of these 2 functions is also a solution to this system. C1, a constant, 1, 2 e to the power 3t plus a constant C2, 1 minus 2 e to the power minus t is also a solution to this system. A theorem. If we have n linearly independent solutions, then every solution can be written as a linear combination of these solutions in exactly one way. Same idea as in chapter 3. So in this case, we can say that our linearly independent solutions form a fundamental set of solutions, and we can say that C1x1 plus C2x2, etc., is the general solution to our linear system. So again, there's nothing new here. We're just using the same ideas as from chapter 3. And now we've come to the end of today's lesson. Tomorrow I'm going to show you how to solve homogeneous linear systems. I'm going to show you what we do if we have complex eigenvalues, and I'm going to introduce the concept of fundamental matrices. And then next Wednesday in the final lesson, we will look at matrices with repeated eigenvalues, and then finally we'll look to see how to solve non-homogeneous linear systems. Are there any questions?